So thank you for the invitation. I hope you can hear me fine. I'm down in Macedonia and Greece today. Wow. So I want to go within the time that I have through some of the slides and take you from what we do in free space optics from inside the satellite, optical wireless to extra satellite, around the Earth to the Moon and to the solar system. You'll find the slides, I just added it here, so you will see half a century of efforts by ESA to promote the technology with several worldwide first demonstrations. So I'll start first with the extra satellite communication, just to, since this meeting is about also optical wireless. And actually, I wasn't sure whether this meeting was also about optical power transfer. So I didn't put anything, but keeping a note that it exists. So if we are in the low Earth orbit and you observe the Earth with any kind of scientific instrumentation, you have two ways of relaying the data into the ground. The one is to use space assets, basically to relay via a geosatellite, which is at 36,000 kilometers, whereas the LEO is less than 1,000. You need 3 of them for the full coverage of the Earth. So basically, you do not require any really substantial ground infrastructure other than the RF stations. Of course, we are limited by the RF downlink. The alternative is to disperse a network of optical ground station around the globe, and then whenever store the information while your instrument produce data, and then whenever you have good weather conditions, start dumping the data with high-speed optical links. The advantages of the one and the other options are clear. The one needs space assets and not really ground assets. The other needs only ground assets, but not really space assets. And the big thing is the high capital expenditure for setting up this global network of OGS. Companies that look at the latter, they adopt the so-called new space logic, who basically is let's do things fast and cheaper, and if they break down, well, we launch another satellite because these are small satellites. And we had the opportunity in 2016 to launch the first data relay satellite system, which is the European Data Relay System, the EDRS, and you can see the logo up here. Now, moving forward, we are trying to integrate the space as an integral part of the global telecom infrastructure, including terrestrial and submarine cables. The logic is very simple. If some of you are in the 50s like I am, you may remember in Europe the MTWM race program, which was the multi-wavelength transport network. Well, this is an extension in space, and we need all the technologies that enable this. So it's terabps data rates with modern coherent transmitter receiver. So if some of you deal with this, then think whether you want to do some thermal vacuum tests and some radiation tests to see how they, if by any chance they can be radiation hard. It's doubtful, but you may be like it. WDM transmission, on-board routing, optical or electrical, very high power optical amplifiers in space, and that's very challenging for when they operate in thermal vacuum. Keep in mind that if you leave any milliwatt unmanageable, it will go adiabatically to heaven. But most important, to integrate the space with the ground infrastructure, you need the up and down links, and that's not easy at all because we are impacted by the atmosphere, so you cannot beat this per se, so you cannot go through clouds, maybe through thin clouds, so we are open to see their solutions. We need adaptive optics, we need pre-compensation techniques. This is a big field of opportunity for many of the companies, so we're very open to see this technology evolving. Moving further away, actually, the Lunar is less than 500,000 kilometers away. We used to consider it deep space. With the development we have now, we even had the protocol coming out of our committees, the interagency committees that define protocols for deep space communications. We abandoned this because we think that we can do now multi-gigabps using the the products that our companies have developed for Earth orbit scenarios. So again, power efficiency is very important if you operate into space, especially if you are far into the moon, either on the surface or orbiting the moon. And the main thrust now for us is to qualify the existing commercial products to operate, to adapt them rather, to operate for the moon distance. Next frontier is the deep space. We class as a deep space something that is beyond the Earth orbit defined by the moon. So the most challenging mission is the one with psyche like psychology, into a metallic asteroid that is trajectory, obviously it varies, but can go half a billion kilometers away from the Earth. And that mission was conceived, I understand, by the University of Arizona and is implemented by our colleagues at JPL at NASA. So we have signed a collaboration agreement. And through our big telescope in Helmos in Peloponnese in Greece of 2 meters, we will try to receive signal from Psyche as far as almost 400 million kilometers. And from another telescope that is about 30 or 40 kilometers in line of sight apart from Helmos, we will transmit a high power 7 kilowatt laser to Psyche. So as you know, the distance in Psyche represents more or less the distance to Mars, which is a very busy target for space missions. But in paper, we already look at missions to Saturn, which I think they set the final frontier for optical communications into the solar system and planetary missions. That's all from me. On the extra satellite communications, I want to close this presentation referring to the diffuse optical wireless communications. A satellite is compartmentalized something like this. The idea here is to try to expedite the way that satellites are integrated and assembled, integrated, and tested. Using fridge magnet type of optical wireless transceivers that they can, by reflections, they can allow communications between remote terminal units that they have sensors, for example, and the onboard processor would expedite the assembly integration testing, which is a big cost factor for satellites. Intra-cavity, we have solutions with repeaters that they can have. So if anyone works on optical wireless, please keep this in mind as a potential solution. Strangely enough, here a key technology will be the batteries, because then we don't need to power these devices. We can use only batteries, and then we have to work out the numbers to see what's the lifetime that we're able to achieve. That's all. To all the community that has been working tirelessly over the years, all credit goes to them. Thanks.